was actually created 100 years ago by Fatou and Julia in France. I have an interesting story to tell about that. There is one of the greatest complex analysts of the 20th century, Alfors. Alfors told me that when he was a graduate student, his professor, Lindelof, made him read the works of Fatou and Julia, which were then the prize essays in mathematics of the French Academy of Sciences. And he read them, and he thought they were the pits of complex analysis, just the worst thing ever. And he also told me that he only understood what Fatou and Julia had been trying to say when he saw the pictures that Mandelbrot and I were showing him. And that goes to show that those pictures are not just hype. They were absolutely essential for even somebody like Alfors to understand what the subject was about. So it's also not true that even in recent times, I'm the creator of the subject. There are also Douady, my own thesis director, and Thurston and Sullivan, who even way back in 1980 were among the creators of this field. So I should give credit to Douady, Sullivan, and Thurston for having inspired this entire subject. So this lecture is about dynamical systems, and for this subject, for this course, a dynamical system is a space X and a map F, which definitely goes from X to X. And you know that you're studying dynamical systems when you're asking the following question. How does a sequence behave? Now, in general, it is very hard to understand exactly what the word behave means. What question do you ask about a sequence? I should emphasize, it is very seldom that we know what question to ask. It is very seldom that we know how to answer the question, how does a sequence of this sort behave, or even know what the question means. But there is one setting where it really does have a clean meaning. If X equals C, it could also be R, but I won't really talk about real polynomials particularly. And F from C to C is a polynomial. Then there definitely is a question, a form of behavior which is well defined. Behave might mean tend to infinity. That is something which is always meaningful for a polynomial. It is more or less obvious that for any polynomial, if you start with an x0 which is sufficiently large, then x1 will be much larger, and x2 will be much larger yet. There definitely is a neighborhood of infinity such that if you iterate starting at points in that neighborhood, you will tend to infinity. Or, of course, there's the other possible meaning, which is or remain bounded. Well, if you can ask whether things tend to infinity, obviously you can also ask whether the orbit remains bounded. This is called the orbit of x0. So, roughly speaking, today's lecture is about, if I start with a polynomial, for instance a quadratic polynomial, and start making such sequences, when will I tend to infinity and when will I remain bounded? Even that question is hard for polynomials of degree higher than 2, because cubic polynomials, well, x cubed plus ax plus b, 2 complex parameters, the set of polynomials for the set of points that go to infinity, you may have to describe loci in the space of pairs of quadratic numbers. That's R4. There's a lot of room in R4, and things can get awfully complicated. I'm really going to be talking almost exclusively about quadratic polynomials. For quadratic polynomials, well, first, all quadratic polynomials can be written z maps to z squared plus c. It isn't quite true, of course. Quadratic polynomials could be written az squared plus bz plus c. But it turns out that you can conjugate any quadratic polynomial to z squared plus c, and then the c is unique. So the c's, possible values of c, exactly run through all polynomials up to conjugation. And conjugation is really the isomorphism of dynamical systems. 2 conjugate dynamical systems have orbits that correspond exactly. So anything you say about one dynamical system, you can say almost as easily about any conjugate one. So all of my quadratic polynomials will be z squared plus c. Now there is a dichotomy. Here, before I write the dichotomy, for p a polynomial, k sub p is the set of z such that z, p of z, p iterated twice of z, and so forth, is bounded. That's the fundamental object when iterating a polynomial, the set of points whose orbits remain bounded, whose complement is the set of points whose orbits tend to infinity. And trying to understand k sub p is what one tries to understand with polynomials. And I'd like to show you some examples. This space, the Mandelbrot Set space, is a picture of this C-plane. Every point is a quadratic polynomial. And there are some values. Well, there are really only two values where you can easily understand exactly what K sub C is. So the first one is 0. 0 is approximately here. If I had actually landed exactly on 0, so what are you seeing here? In black, you are seeing K sub C. And in color, you're seeing points that escape to infinity. But there is sort of an obvious way of coloring the points that escape to infinity. You might ask, for instance, when is the first time that the absolute value gets bigger than 10 or gets bigger than 100? And in fact, it's 10 that's being used at the moment. If you take a look here at the settings, you'll see that 10 there. That's telling you that the coloring is according to the first time when a point which escapes to infinity actually passes 10. I could change it. Now, that's an exceptionally simple case. But here is one which is a bit more complicated. And I can show you what the iterations look like. That wasn't what I wanted to do. Well, for this particular x0, x1 is there, x2 is there, x3 is there, and you can see that what is happening is that the orbit is being attracted to an attracting fixed point, which is here. And I hope everybody agrees that it's crystal clear from looking at this picture that at least the orbit of this point is attracted to an attractive fixed point, which is there. Whereas if you happen to start outside the Julia set, outside K sub P, then you iterate off to infinity. And you'll notice I was once in this color band, once in this color band, once in that color band, once in that color band. That means that if at this point I take a certain number of moves to reach 10, well then at this point, of course, I've done it once already, so I'm going to take one fewer times, and so forth. Now, this picture isn't all that complicated, but if I were to choose a somewhat more complicated point, like I don't know, this one. And let's go in my settings, and computers being so fast today, I'll iterate 1,000 times. Change the picture slightly. Okay, well, here it is still true that the black is K sub P. If you start inside the black anywhere, you will be attracted to a cycle of period 1, 2, 3, 4, 5, 6, 7. That's the case throughout the black. And on the outside, you iterate off to infinity, although in a more complicated way than before. Now, it is not quite true that all Julia sets look anything like that. I could come up with this one. No, that isn't what I want to do. I want to go to dynamics, and I could come up with this one, or with but there really is a dichotomy, and the dichotomy is that if I chose a point outside the Mandelbrot set, that isn't what I want. Then case of P looks essentially different. And what it is really true is that it is disconnected. For one thing, you can see that it breaks into two pieces, that one and that one. And then this one itself breaks up into two pieces. And then each one of those breaks up into two pieces and so forth. If I make successive blow-ups, you will always see the same, and you will always see many pieces coming together. So, if I make a blow up here, if I make a blow up here, make a blow up here, make a blow up here, you always see the same picture. And what you are seeing is a Cantor set. A set which is compact, and the connected components are points, and there are no points that are isolated. Let me try to explain. So, I said there is a dichotomy. That's the dichotomy. So I'm going to try to explain why this is justified. And I'm going to think that points here, I invite you to check z bigger than 2 implies z squared plus 2 is bigger than z. So if you start outside the circle of radius 2, you're going to go further, and will, in fact, necessarily go to infinity. So I think of these as escaped. Now, where are the points which escape in one move? Those are bounded by the curve of equation z squared plus 2 equals 2. Okay, now, elementary one variable complex analysis. What does the curve of equation absolute value of z squared plus 2 equals 2 look like? Anybody want to try? Any candidates for coming up and showing where the curve of equation z squared plus 2 equals 2 is? What?
Subcurve.
What kind of curve?
A subcurve.
No.
No.
No. No.
It is a cardioid.
No. But think about it. What does the inverse image of a little arc here look like? 0 maps to 2. And what do the square roots of purely imaginary numbers look like? Two lines like this. Oh, you take this, you bring it over here, and you take the square root. And in fact, it forms a lemniscate. And these points can be, so these are the ones who escaped in 0 moves. These are the ones which escape in 1 move. And now, where are the ones that escape in 2 moves? So this lobe, which I hesitate to touch the screen, this lobe gets put like that on the whole circle. And therefore, the points that map to this figure 8 will form 2 figure 8s like this. And now the points, here are the points that escape in 2 moves. And now where are the points that escape in 3 moves? Well, you see two more figure 8s, and here are the ones that escape in 3 moves. And in the final analysis, the points that do not escape, i.e. k sub minus 2, are some dust infinitely deep in all the figure 8s. Now, I was trying to justify the dichotomy that if the critical point escapes, then you have the k sub p is a Cantor dust, and if the critical point does not escape, then the k sub p is connected. And I claim, I mean, one can prove it, but this should convince you that there's a good chance of that. Because what led to breaking up into 2 pieces was that the critical point escaped, and if you start drawing big circles around infinity and taking their inverse images, they will be inside each other, and at some point you'll land on the critical point, and when you land on the critical point, then it will break into 2. And then after that, it'll break into 4, 8, 16, and so forth. And it will land, it's not obvious, but it's true, that the set of points that do not escape will form a Cantor set. And I hope that you find this example convincing that there's a good chance that it's true. So this is the definition of the Mandelbrot set. Okay. So the objective of my lecture is explain the structure of M. It isn't exactly obvious what the word structure means, but I will try to illustrate the meaning as I go along. First, I would like to emphasize that the Mandelbrot set is complicated. So let's take some little place around here. And I'm in Zoom, yes. Okay, there is that blow up. And let's go and look in here. Any place will do. Oh, there's a little Mandelbrot set. What do you know? But let's see whether there's anything else of interest. Let's go and take a look at what's in here. Oh, there's another little Mandelbrot set. Let's go and see what's in here. Okay, maybe this is enough to convince you that the Mandelbrot set is a complicated object. So my objective is to give a name to every dot of the Mandelbrot set. Give a name, and a name which is meaningful for every dot of the Mandelbrot set. Well, every dot of the boundary of the Mandelbrot set. And I intend to succeed. I intend to succeed in giving a name for every dot of the Mandelbrot set that reflects the dynamics of the corresponding polynomial. I had 2 pens, and I've managed to lose one, but I could find the other. So a first statement is M is connected. Now, if you remember the Riemann mapping theorem, you will realize that this is equivalent to there exists phi sub m from C minus m to C minus the closed unit disk, analytic isomorphism. If M is connected, then the Riemann sphere minus M is simply connected, and therefore, by the Riemann mapping theorem, is isomorphic to the disk. You can send well, let's think of the exterior of the disk, which is also a disk, and let's send infinity to infinity. Then, now, finding conformal mappings, how many people have taken a course in complex analysis and have discovered how remarkably difficult it is to write even the conformal mapping for the complement of a square or something? Finding conformal mappings isn't easy. But as it turns out, the way we prove that M is connected is by computing the Riemann mapping, and amazingly enough, it's easy. So I will now illustrate it for you. I will illustrate the conformal mapping of the complement of the Mandelbrot set. Okay. The reason for which I am bringing up this picture is to draw this set. C minus the closed unit disk. You can see it there, but you can do much better than just see it. You can see R e to the 2 pi I theta with theta written in base 2. Do you see that picture? This point, for instance, well, maybe I'll use this and see whether I can say this point. What is its external? What is its theta? It's e to the 2 pi I times 0.01 0.01001. By following in and interpreting the yellow as 0 and the blue as 1, you can read off in base 2 the angle of the point where you are. This picture allows you to read off the coordinate of C minus d bar both radial and especially angular. The angles are measured in turns and are written in base 2. Now, we go to this picture, and tra-la, you are seeing the conformal mapping of the complement of the Mandelbrot set. You are seeing the radial lines, and you are seeing the angles of various points. So let us try to contemplate what the angle of the ray that goes there is. So far, what can you read? You can read point 0.001 001. Shall I do that again? 001 is what you'd have to start further out to see the first two zeros. But 001, this blue is that one. Then 001, 001, and if I do a blow up, you can clearly see 100, 100, 100, 100, 100, 100, 100. It seems perfectly clear that this angle Now, you agree or you don't? Do you think it's true? At least, I claim that this picture clearly justifies it. And what number is that? Who knows how to figure out how to read repeating binary sequences? As it turns out, this is 1/7. But it's also 1/2 cubed minus 1. This 3 is the same 3 as the 3 with which the orbit repeats. And as it turns out, 2/7 is here. 3/7 is here. 4/7 is here. And as you might imagine, five-sevenths is here, and 6/7 is there. Now, what is special about 7? Well, what's special about 7 is it is 2 cubed minus 1, and the cubed has a 3. And in this domain, there is a periodic cycle of period 3, and here there is also a periodic cycle of period 3, and there also. Now, as it turns out, here is where the cycles of period 4 are. there's a cycle of period 4 here. There's one here. There's one here. There's one here. Then there's one here. And there's one here. And this is 1/15, 2/15, 3/15, 5/15, 4/15, I'm sorry. And then you come to 5/15, but as it turns out, 5/15 is 1/3, and we've already seen 1/3, which is here, because this is a region where there is a cycle of period 2. 6/15 is here. 7/15 is here. 8, 9, 10, which doesn't count, because 10/15 is 2/3. Then 11, 12, 13, 14. Now this is what I mean by the structure of the Mandelbrot set. We understand exactly where the external rays of the parameter of the conformal mapping of the complement of the Mandelbrot set go, and they are related to the dynamics of the polynomial at the end. For instance, I, the complex number I, is something like, is about here, and is at the end of the array of angle 1/6. Now, it's kind of fun to draw the Julia set for z squared plus I. The Julia set for z squared plus I looks something like this. And 0 maps to I, maps to -1 plus I, maps to minus I, maps back, so this maps there, which maps there, which maps here, which maps there. It is indeed true that 0 squared plus I is I squared plus I is -1 plus I, -1 plus I squared plus I, well, I bet you can all compute it, but maybe you don't do it in your head. But it is in fact minus I, and minus I squared plus I is again -1 plus I. Now 1/6 is equal to 0.001, which repeats in base 2. And you'll notice the digits after one term repeat with period 2, and the critical point after one move repeats with period 2. There is this extraordinary numerology that the digits in base 2 of an external angle, written in base 2 and counted in turns, reflect the dynamics of the polynomial at the end of that ray. That is what I mean by giving a name to each dot of the Mandelbrot set. Each dot of the Mandelbrot set, it has as its name the development in base 2 of the external ray that lands at that point. That's the name of that point, and the sequence of digits reflects the dynamics of the polynomial at the end of the ray. And this is a clear example of that sort of phenomenon. Well, I think I will stop here.